Engineering Department at Memorial University of Newfoundland. And the title of my talk today is Hybrid Quantum Classical Computing for Internet of Everything Optimization. So it might sound a bit wordy at this time, but I will break down each term one by one. Okay, so the outline of today's talk includes a brief introduction to Internet of Everything and quantum computing. I will briefly discuss the present landscape of quantum computing. I will discuss some of my current research, and all of these research projects in the core are optimization problems, and I will also like to discuss some future research prospects as well. Okay, so the term IoE, short for Internet of Everything, is basically a broader concept of IoT, which is Internet of Things. While IoT or Internet of Things only focuses on connecting devices, IoE goes beyond pure device connectivity. It aims to connect four different components that are data, people, object, and processes. So under this huge IoE domain, my research so far has been focused in three application areas. The first one is network function virtualization, which is basically the concept of softwareizing network functions such as firewall. And then there is another application area called metaverse, which is basically extended virtual reality. And finally, connected autonomous vehicle, where the vehicles can sense and operate on its own without any kind of human involvement. Okay. So before going any further, I would like to discuss why do we need quantum computing for such application areas. Today's network can handle about 10 milliseconds of latency. However, in order to achieve instant communication in more sophisticated IoE domains such as metaverse, tactile internet, connected vehicles, what we need to have is much lower latency and much higher bandwidth than what we have available today or than what is possible with with today's classical computer. So we need to optimize things further beyond the capacity of today's classical computers. Okay. So in this slide, I will draw a very brief comparison of classical versus quantum computing paradigms to solve optimization problems. Traditionally, in the classical computing paradigm, these problems are approached with traditional mathematical programming frameworks, such as integer linear programming, mixed integer linear programming. However, those are usually NP hard, and the computational complexity grows exponentially with the problem size. So not quite scalable. And then there are some approximation algorithms such as meta-heuristics and heuristics, and those are simply not fast enough to keep up with the latency or delay requirements of the futuristic IoE applications I'm working on. And then there are some traditional AI techniques such as reinforcement learning, neural networks. However, these require frequent retraining because the network conditions change too fast. Moving to the quantum side, we have some popular quantum optimization algorithms such as quantum annealing, which is supposed to be faster than classical algorithms, and they are also known to provide reasonable optimality gap. Then there are some quantum AI techniques or machine learning techniques that are supposed to require less trainable parameter compared to classical machine learning. So they are able to learn faster and better with fewer data compared to classical counterpart. Now here you might think that learning and predicting with fewer data means overfitting on the data, but it's not quite the case in quantum here, because as per Holder's theorem, it has been theoretically proven that quantum AI techniques are inherently prone to avoid any kind of overfitting. Now, as good as everything sounds about quantum, the biggest question is, are we really ready for the quantum computing revolution yet or not? My answer to this question is rather on the gray zone. So it's yes and no at the same time. We do have some quantum computing resources available in today's world. However, those are simply not fast enough. They are simply not enough to keep up with the scalability requirements. So we cannot solve very large scale or reasonable scale optimization problems with quantum computing yet. So here my research comes into play. I try to combine hybrid and classical algorithms in such a way that I can merge the advantages of both of the computing worlds, basically to help the case of optimization problem. Now, I'd like to mention that quantum computing isn't a myth anymore. Ericsson has recently established a quantum research hub in Canada for communication optimization problems. The government of Canada has several quantum-specific grant calls to strengthen Canada's quantum research and innovation capacity. In Japan, they have been using quantum computing to optimize their marketing and advertising and communication strategies. Quantum optimization technique was applied at the port of LA for some container optimization task that made improvements worth of millions of dollars. And all the luxury vehicle companies such as Rolls-Royce and Mercedes are also opting in for hybrid quantum optimization techniques to build better electric vehicles. And quantum computing is even at groceries as well. So Save-On Foods in Canada have been using quantum computing to bring down their staff scheduling task from 25 hours to just 2 minutes, which is quite impressive in my opinion. So all these efforts basically show that we have been progressing towards the quantum computing era with the help of various quantum computing vendors such as AWS from Amazon, Xanadu, OneQubit, D-Wave, IBM's Qiskit, etc. Throughout my research, I have been trying to figure out the answer to these three following questions. The first one is, what are the advantages of solving these optimization problems with quantum computing? What are the major trade-offs that we may face and that may challenge the applicability of this technology? And finally, what are really the differences of quantum versus classical computing when it comes to solving optimization problem in terms of found solution quality and computational time? So these are the main major three key questions that I had in mind when I started my research with quantum optimization. Okay, so from the slide, I will very briefly discuss how quantum computing is actually different from classical computers. So as we know that the fundamental unit of information for a classical computers are bits, right? But in quantum computer, they are called qubits. Now, these qubits have few special mechanical properties, quantum mechanics properties. The first one is superposition, which is basically the ability of quantum system to coexist in multiple states at the same time. So, for example, a bit in a classical computer is either 0 or 1, right? But a qubit can be 50% of the time 0 and 50% of the time 1. We really don't know until we measure it. And this enables massive parallel computing power for qubits that makes basically massive parallel computation easier for quantum computers, which makes quantum computers to reach solutions faster than classical computer. And then there is quantum entanglement, where two qubits are so strongly correlated to each other that they can gain almost instant information about each other without having any direct communication in between them. So this is again useful for optimizing communication. Okay, one of the most popular quantum computing algorithms, optimization algorithm is called quantum annealing, and it's basically a meta-heuristic search algorithm for finding the lowest energy level of a quantum system. So the algorithm basically works like this. Uh, Initially, all the qubits in a quantum computer are in superposition state. So, without any external force being applied, the probability of these qubits either falling into zero or falling into one remains 50-50, equal. However, things get interesting here. We can apply some external magnetic force, and basically we can tune these probabilities in such a way that it reflects the criteria or the search space of our optimization problem. Okay. And then what we can expect is that the optimal solution or the best possible answer will lie at the very bottom, and the quantum annealer will be able to scan the search space and settle down at the lowest energy level of the search space or of the quantum systems, which is our desired solution. Okay. So whenever we work with an optimization problem, we start with the objective function that we need to optimize, right? So let's say we have an objective function like this one here. And in order to make it compatible with quantum annealing, we have to first make it in a quadratic unconstrained binary objective function. So let's say we have this objective function. Now what we have to do is we have to render it as a triangular graph where each nodes of these graph represents qubits of quantum computers. Okay. And the edges between them basically represents the coupler strength of those qubits, how strongly correlated they are, and the bias of these nodes or qubits and the edge weights are basically set as per the quadratic and linear coefficients of the objective function that we have at hand to solve. So we prepared this graph and then we basically map it into a quantum lattice structure. And then the annealer basically sees it as an energy landscape and tries to traverse the search space and get to the optimal solution. While trying to get to the optimal solution, it uses a special effect called quantum tunneling. And I can explain this phenomena in a very simple way with an analogy. If we throw a tennis ball at a wall, what is likely to happen? Can anybody answer from the audience?
It will bounce back.
Of course, it will bounce back. Thanks for answering. But in quantum world, it is supposed to penetrate through the wall because it can overcome higher energy barriers because of the special quantum mechanics properties. And that's how actually quantum annealer is able to overcome local suboptimal solutions and get to the optimal solution very quickly, faster than classical computers. And at the end of the annealing process, we read out the solution classically into the qubits. Okay, so that's what quantum annealing is. Now, you probably must have already understood that the size of the problem and the number of qubits required to solve those problems are definitely correlated, right? So the bigger the objective function is or the optimization problem is, we need larger number of qubits. However, unfortunately, we do not have such high number of qubits available in today's quantum computers. So here what I do is I try to combine classical and quantum algorithms. Basically, the idea is to shrink the number of quantum resources or qubits so that we are able to solve at least reasonable scale optimization problems. So we call this technique warm start quantum annealing. It's a hybrid approach where we kickstart the optimization or the search engine with a classical algorithm such as simulated annealing, and then we quickly shift our gear towards quantum annealing. By combining both of these techniques, our aim is to solve the optimization problem faster than classical algorithms, and we are also able to solve reasonable scale or intermediate scale optimization problem that are not possible with standalone quantum computers. So speed gain and scalability is the major key metrics here. Okay, so now I will explain a few projects, research projects where I have applied quantum annealing. The first one is service function chaining, where we let the internet traffic steer through multiple layers of network functions such as antivirus, intrusion, security to get a particular service in the IoT network. And the objective function has been to minimize the overall resource utilization. By resource, I mean CPU, RAM, and bandwidth costs. And like any other objective function, it has a couple of constraints. For example, capacity constraint, hardware limitation check, and even path validation, those kind of things. So the proposed methodology here was warm-start quantum annealing that I just described in my previous slide. And what we have been able to achieve is better scalability compared to standalone quantum annealer and better resource utilization compared to classical counterpart. So here are some sample results. So as the problem size grows, if we compare the optimality gap, we can see that warm start quantum annealing, which is the hybrid technique, and the standalone quantum annealing perform quite comparable to classical algorithms. However, they perform much better when it comes to running time. So standalone quantum annealer provides the fastest solution, and warm start quantum annealing, which is the hybrid technique, lie in between classical and quantum algorithms. So we have some kind of speed gain advantage. Okay, so in the second project, which is metaverse resource optimization, we proposed this metaverse slicing framework, which is inspired from traditional network slicing. Here we have each meta slice dedicated for supporting different kind of virtual reality applications such as travel meta slice, education meta slice, and navigation meta slice. And there are some common shared function. For example, Google Maps API can be shared for virtual reality live location sharing, check-in, and routing purposes. And we also make sure that the delay-sensitive resources are placed or deployed at the edge of the network in closer proximity to user, and the not so delay sensitive applications can go to the cloud, which is further away from user. And that's it. The objective function or the problem statement is that we optimize these resources in this multi-tier architecture to ensure timely content delivery. And here, in terms of methodology, along with warm start quantum annealing, we also proposed cold start quantum annealing, where we start with quantum annealer instead, and then post-process and fine-tune those solutions using simulated annealing. So basically, we wanted to observe what happens if we do vice versa. So some of the sample results look like this. In terms of optimality gap, both the warm start and cold start quantum annealer perform quite comparable in terms of solution quality. However, the cold start quantum annealer and the quantum annealer are the fastest. The warm start quantum annealer performs a little lower compared to the standalone quantum and cold start quantum annealer approaches, but it is significantly better than classical algorithms. Finally, we also make sure that all the real-time resources are being deployed at the edge, and the semi and non-real-time resources are placed into the cloud to basically make sure that our optimization model is working well. However, we do notice a slight difference in terms of scalability. Warm-start quantum annealing are much more scalable, 20 to 30% more scalable compared to quantum approaches where we start with quantum annealer, right? But they perform not as good as them in terms of running time comparison. Okay, so in the third research project, I have used again quantum annealing, but not quite for the reasons that we have been using it so far. So think about this framework here. Whenever a network component in a IoT substrate graph fails, we need to redeploy a recovery instance, right? But by the time we redeploy a recovery instance after a failure, the situation becomes uncertain, the network condition changes. So there are some uncertainty going on with the redeployment cost of those network components. And in such cases, what we prefer over optimal solution is robust solution. Okay. So by robust solution, I mean that the search space has an uncertainty bound to it, right? But the robust solution is the one which has narrow range of uncertainty around it. And that's why it is the robust solution, because it will work well under different uncertainty settings or scenarios. So in this case, we have proposed a robust optimization model that improves reliability in post-failure network function scenarios by considering uncertainty. And we have proposed two kinds of solution. One is fully classical, where we have utilized the But-SIM technique proposed by the MIT professors. And this technique is immune to worst case scenario, and it has a parameter that we can tune as per the affordability of our budget, as per the affordability of risk that we are willing to take. So we can adjust the budget of uncertainty in this formulation, which is a nice thing to have for service providers. But on the quantum side, what we have been able to observe is that possibly due to creating a flatter minima, the nearby solutions are much closer to the robust solution. So quantum mechanical nature actually explores multiple configurations simultaneously and parallelly and finds solutions inherently that are more resilient to changes in the input data. And that's why the quantum annealer can actually generate or actually find inherently robust solutions because of how it creates the search space. Looking at the results, we can see that even when the uncertainty, like that we have some uncertain parameters and it deviates by 10%, 30% or 50% from their nominal ranges. And even with growing uncertainties, if we look at the minimum and maximum cost range, it will give us idea about the reliability of the approach. So we can see that even at the highest peak of uncertainty that we have considered, quantum approaches give higher minimum and lower maximum cost with a narrow range, which basically means that they are less prone to changes or significant changes in the face of uncertainty, so they are more robust. However, if we compare the running time, we can see that after the network size grows beyond 100, quantum annealer cannot generate any solution at all because we don't have enough available qubits to simulate those problems, right? So in that case, we always have to turn into classical approaches like robust optimization techniques that we discussed. Okay. And in the next part of my talk, again, I have tried to solve different kind of optimization problems where we adopt the strengths of quantum AI techniques. So the first project was this one. It is basically the framework of metaverse data marketplace trading. where we have a few key players. The first one is metaverse infrastructure service providers, and they basically collect some virtual reality data and they sell those anonymized data or data-based services to data consumers, and in exchange they receive some kind of incentives or payments. But the unfortunate thing is that metaverse service structure providers uses edge IoT devices and cloud servers for storing or processing those data, but those devices and cloud servers are not directly owned by them, right? So what they need to do is they need to subscribe to those edge or cloud resources well in advance before observing the demand of those data or database services, right? So what they can do basically, they can subscribe to those resources via two schemes. The first one is reservation stage, where they haven't seen the uncertainty or actual demand yet. So they take a guess and subscribe to some resources. However, if they do not approximate those resources correctly, for example, if they undersubscribe, they have to purchase additional resources at a more expensive price in the on-demand stage. Also, if they oversubscribe, there will be some wastage of resources, right? So there is some uncertainty going on with the decision making at this stage. And here we have proposed a stochastic integer programming framework, which basically incorporates multiple discrete uncertain scenarios and then optimizes the cost of that and tries to take decisions accordingly. However, the challenge is that as the number of uncertainty grows, the computational complexity of the stochastic integer model will grow exponentially as well. In that case, what we can do is we can actually use quantum neural networks to predict the demand, which narrow down the uncertainty space of the stochastic integer programming model. And that helps the case of computational complexity as well. So you might ask that why are we not using artificial neural networks to predict the demand? So my answer is that being a very contemporary domain, such as metaverse, we have very limited availability of data. And quantum neural networks can actually learn and predict better with fewer data compared to artificial neural networks. I will show some results in the upcoming slides. But the objective function kind of look like this. It has two parts. The first part basically calculates the reservation phase cost, and the second part calculates the on-demand cost. Under the on-demand phase, we have a set of uncertain scenarios. We also know the probability or likelihood of happening those scenarios. Then we basically multiply that and calculate the overall cost and tries to minimize the overall cost, right? But as I have been saying, the search space grows as the number of uncertain scenario in the on-demand phase increases. And that's why we have a quantum neural network here. I will try to basically highlight the differences of classical neural network and quantum neural networks in this slide. So what is the key part of a classical neural networks? We have some linear transformations and some nonlinear activation functions, right? In quantum neural networks, we basically reflect those using displacement gates, some Gaussian and non-Gaussian gates, and the neural networks have some weights that we need to adjust for learning. Likewise, in the quantum computer, we have some gate strength parameters that reflects the weight parameters, and some of the quantum properties like entanglement and superposition that I described earlier in my slides cannot be simulated in the classical neural networks at all. Okay, so as per the results, we can indeed see that quantum neural networks have been able to learn better with fewer data. It has been able to minimize error at a fewer epochs, which is great. And even under growing uncertainty, we can see that our proposed quantum-assisted stochastic integer programming technique has been able to adapt its strategies even with the growing uncertainties. And as for running time, we can see that the quantum-assisted technique outperforms all other approaches. We have considered some baseline approaches such as EVF and stochastic integer programming approaches that are traditionally used to solve optimization problems with uncertainties. And this is basically the last research project that I'm going to describe, which was done in collaboration with NRC and their connected and autonomous vehicle team. And this research project is about optimizing vehicle platoon. And a vehicle platoon is basically a collection of vehicles that move together in a coordinated manner, and they exchange some information in between them. Also, they exchange some information with the roadside unit. So the communication between vehicles is called V2V communication, and the communication with the roadside units are called V2X communication. And NRC is also emphasizing on quantum solutions. What we are trying to achieve here is string stability, so we can make sure the platoon structure and their communication is more efficient. In this project, what we have done is we have used different kind of techniques. We have first of all used quantum long short-term memory that is able to predict the future behavior of nearby vehicles based on their actions and sensor data. We have also used model-based communication strategy, which is basically used to maintain optimal inter-vehicle distance and speed synchronization. And we have also used event-triggered communication, which basically sends current state of a vehicle to neighboring agents, only if the kinematic model since the last broadcast is still not accurate, to minimize the communication policy or strategy. Okay, so the overall objective is to minimize the efficiency cost and maximize the stability, minimize total energy consumption, and maximize communication and minimize communication latency and cost as well. Okay, so in this research project, we have two modules. The first one is prediction modules, which has a quantum LSTM model that analyzes the historical states and make prediction for the leader vehicle. Okay, and then this predictions are passed down to the second control and communication module, where we use these predictions. We have some objective function and constraints, and the optimizer basically tries to generate control signals for the vehicle by taking into all these into consideration. And also these control signals are passed down to the nearby vehicles through V2V communication to basically optimize their control strategy as well. Okay, so the quantum long short-term memory has basically three parts. The first part, which is the encoding layer that transforms classical data into quantum data. The variation layer, which basically has some forget block, input, output, and update block. So this basically tries to decide how much information to retain from previous iteration and how much to forget to basically update the circuit. And finally, we have a quantum measurement or output layer. For the results, we can see that the QLSTM actually is able to learn faster than classical LSTM technique. If we look at the performance of the vehicle, we can see that the QLSTM actually outperforms classical LSTM. However, regardless of LSTM or QLSTM, with the growing number of vehicles, the error level increases because of cumulative error. And finally, we can see that our proposed QLSTM is able to maintain its performance in terms of speed and acceleration, even at reduced communication scale. So even if there is minimal communication or optimal communication between vehicles, it is able to maintain that string of the platoon. Okay, so this was all of the research projects that I wanted to discuss, and I get this question a lot, that how have I been implementing the quantum techniques that I have discussed. So I have used D-Wave for quantum annealing. They have a quantum hybrid optimization solver that is available via cloud. And for quantum machine learning and AI approaches, I have used Xanadu's Quantum Cloud. And then there is IBM's Qiskit, Amazon Bracket, and Quantinuum for QNLP and other tasks. These are some of the publications that are relevant to the research projects that I have discussed so far, just in case you are interested and want to explore more. And basically, to summarize things, the positive impacts of these kind of work is that we get to observe the quantum speed up. We are getting quantum ready for futuristic IoT application. We are also evaluating the potential viability of quantum optimization approaches. Some of the challenges are how can we design the quantum algorithm or the quantum or QB formulation in such a way that it is understandable and solvable by quantum computer. It's not quite the same case for classical algorithm. And then there are some lack of open source quantum resources to basically learn and implement these strategies. And then there are also some memory issues if you want to simulate quantum states in your local system. So it is not quite feasible, right? And there are infeasibility for solving large scale optimization problems with quantum computing, where we are trying to adopt hybrid approaches. And finally, some of my future research directions are distributed quantum computing and quantum resource estimations to solve these problems more efficiently. And some of my future research projects that I'm working on is basically digital twin decarbonization and mobilization with quantum optimization techniques, EV electric vehicle charging, optimal charging schedule generation with quantum computing, predictive maintenance, because we don't have enough faulty data of an industry or a process or manufacturing process, right? In that case, quantum machine learning can be useful because it can learn even with limited or imbalanced data, right? And finally, I have also been working on optimizing the cohort for clinical trial optimization with quantum annealing, which has some advantage to offer. And finally, my larger research vision is to incorporate my research in this smart city landscape where some of the urban living element will be impacted and enhanced by some kind of quantum optimization or quantum machine learning technology. And these are just my 2 cents that I would like to share while I was in my quantum learning journey. So it's a marathon journey, just like any other emerging technology. We need a lot of patience. And in order to sustain innovation at this current stage, what I believe is we need to approach diversity in methodology. So we need hybrid approaches to really see the advantage at this moment. That might not be possible with standalone quantum approaches. And then our efforts must go beyond financial means, and we need some quantum skilled workforce at this moment to progress towards the quantum vision, right? And finally, what I want to say is that quantum advantage is problem specific. We probably should not consider it or even implement it for solving any or every other tasks. So the advantage is really problem specific. We really need to make sure that the quantum advantage that we are getting is well worth. And finally, I would like to acknowledge the following that kept me motivated and gave me enough support to learn this emerging technology during my PhD journey and so forth. Thank you so much.
Okay, thank you very much, Dr. Emu, for your insightful presentation and great slides. So the floor is now open for questions. If anybody has questions for the speaker, you can put them now. Okay, so maybe I will begin with you presented very interesting, concluding slides in which you talk about platooning, autonomous and connected vehicles platooning. So are you investigating this system at, at vehicular level, or you are looking at more of a macro level where everything is modeled as, fluids or traffic flow, and then you are not looking into the, precise details of each and every vehicle where, uh, uh, you know, uh, so that we are not talking about lane changes or takeover of vehicles with each other, but more as how vehicles move together as a group and looking at average speed and average braking power and so on. So if you could elaborate on that.
Yeah. Thank you for the interesting question. It is more the later case at this moment. So currently, I'm just looking at like assuming the assumption is that how can we maintain average speed and acceleration to maintain that plateau string independent of other vehicles impacting those.
Okay. And it is also very interesting to see that many of the problems you presented, we are also approaching them, however, from a different methodological point of view. So many of the PhD students of mine who are working on autonomous vehicle platooning or smart city and digital twins are here, and they have just started their work, and they are also looking at AI-based models to address some of these questions. So continuing in the same thought, when we apply this quantum perspective, you also mentioned that we have to think differently. So if somebody is doing traditional optimization modeling or simulation modeling and not using this quantum approach, then if they want to transition to your way of looking at things and solving the problem, what are the changes they need to know, or how should they prepare so that they are not confused between the established methodologies and the new quantum techniques?
Yeah, that is also another interesting question, and I do acknowledge that there aren't enough resources yet to transition our classical optimization research into quantum domain. So first, I think the first step is basically to learn the basic quantum algorithms and things how they work. And I think then the next step will be to basically investigate how can they map it accordingly that can suit the needs of their problems. And the final stage will be really to have some kind of discovery or even some kind of findings that if it is providing any advantage at all. In most of the cases, at this time, probably the standalone quantum algorithms won't be able to provide any advantage. The students might consider thinking that how can I combine that with other kind of classical algorithms or the algorithms that I'm working on, or even solving a critical part of the optimization problem with the quantum computing technique and leaving the rest of the problem for the classical part. So maybe these are the approaches that can be solved for the similar kind of problems that the students might be considering their research.
Okay, so my last question is about the NRC team of automated and connected vehicles you mentioned. So could you throw some light on this? Where are they and what are they doing? Are there any pilots in Canada for such vehicles? And
Okay,
where is
yeah.
funding?
So the team that I have worked with is the team leader is Dr. Rahman, and the team is in London, Ontario. So they actually have a plan to, they have bought the vehicles, but they actually have a plan to basically implement it in actual route to see the impact of the strategies they have been working on. This is just one part of their research, but yeah, they have some autonomous vehicles and they have plans to implement that on the actual roads.
Very good. So are there any other questions from the audience uh, who would like to know about the quantum way of addressing the problems Dr. Emu mentioned? Okay, so if there are no other questions, you can always write to her or write to me, and I will put you in touch with her. She's doing great work, and I think we are also trying to be in this direction, and we will contact Dr. Emu for her advice on these. Thank you very much, Dr. Emu, for your insightful presentation, and we look forward to have you at another course event in future. Thank you once again.
Thank you so much for inviting me and letting me share my thoughts on my research. So thank you again. Bye.
Okay. Thank you, everyone, and have a great day. Bye-bye.